Every advanced AI chip begins with a machine that almost nobody has ever seen. Without it, Apple, NVIDIA, AMD, Intel, and TSMC compete to build the world's fastest processors.
The processors powering artificial intelligence contain features so incredibly small that ordinary manufacturing methods simply cannot create them.
Modern transistors are measured in billionths of a meter. Manufacturing them requires a level of precision that once belonged only to science fiction. To create patterns this small, engineers first had to solve one of the greatest optical challenges in human history.
For decades, many experts believed the solution simply could not be built. The laws of physics appeared to stand firmly in the way.
Yet a small group of engineers refused to accept that answer. They believed impossibility was simply another engineering problem waiting to be solved.
Their invention would eventually become one of the most sophisticated machines humanity has ever built, and almost nobody outside the semiconductor industry even knows its name.
The story doesn't begin in Silicon Valley or Taiwan. It begins in the Netherlands, where few imagined origins.
In 1984, a new company was formed with a simple objective: build lithography systems for an industry already. The company had limited resources, little market influence, and no guarantee of survival. Many believed it would simply disappear like countless other technology startups.
The competition already possessed decades of experience, global customers, and enormous research budgets.
At the time, semiconductor manufacturing was advancing rapidly. Every new generation demanded greater precision than the previous one.
Every improvement created a new problem. As chips became smaller, manufacturing them became exponentially more difficult.
The challenge was no longer building better machines. The challenge was overcoming physical limits that seemed impossible to defeat.
That small company was called ASML. Few people noticed its arrival. Fewer still believed it would help define the future of technology. To understand why ASML became so important, we first need to understand the problem every chip manufacturer was desperately trying to solve.
A single human hair is roughly 7,000 nanometers wide. Today's advanced transistors measure only a tiny fraction of that size.
As engineers reduced transistor sizes year after year, a new obstacle appeared. The machines responsible for the problem was surprisingly simple. Light itself was becoming too large to accurately print features that had become unimaginably small. For decades, researchers improved lenses, mirrors, and manufacturing techniques. But every improvement only delayed the...
Some experts believed the semiconductor industry was approaching a wall that no amount of engineering could break through. Progress itself seemed ready to slow down.
Yet a handful of engineers refused to accept that conclusion. If existing light could not solve the problem, perhaps an entirely different kind of light could. That single idea would eventually trigger one of the most ambitious engineering projects in modern history. The answer wasn't building a better machine. It was creating an entirely different kind of light, one that almost no factory had ever attempted to control. The new approach relied on extreme ultraviolet light, often called EUV, because its wavelength is much shorter than ordinary. But the breakthrough created an even bigger problem. Unlike ordinary light, EUV cannot travel through normal air. Everything the semiconductor industry had relied upon for decades suddenly became useless. Engineers would have to rethink the entire machine from the ground up. If lenses could no longer be used, only one solution remained. Every beam of EUV light would have to be guided using mirrors polished to an almost unimaginable level of perfection. These were not ordinary mirrors. Even microscopic imperfections could distort the light enough to ruin an entire semiconductor wafer. Inside a single EUV machine, the light must reflect across multiple mirrors without losing its precision. The semiconductor industry was no longer trying to improve an existing technology. It was attempting to build a machine many physicists believed should never work outside a laboratory.
By the late 1990s, ASML faced a decision that would define its future.
Einstein. The proposal demanded years of research, enormous investment, and no guarantee of success. Even inside the company,
every simulation revealed new obstacles. Solving one engineering problem often uncovered 3 more waiting behind it.
The project consumed time, money, and patience. Years passed while progress remained painfully slow.
This challenge had grown beyond one company. It demanded expertise in optics, software, mechanics, electronics, and materials.
Some components required manufacturing accuracy measured in fractions of a nanometer. At this scale, even the slightest imperfections.
What looked like slow progress from the outside was quietly becoming one of the greatest engineering efforts in semiconductor history.
Designing the machine was only half the challenge. Building the optical system demanded a level of precision that no single company could achieve alone. ASML partnered with the German optics company Zeiss, whose engineers had spent decades mastering some of the world's most precise optical technologies. Because EUV light cannot be focused using conventional lenses, every reflection had to remain almost perfectly accurate throughout the entire optical system. Even a microscopic vibration or temperature change could reduce accuracy. Every part of the machine had to operate as one perfectly synchronized system.
Generating EUV light required another remarkable breakthrough. Tiny droplets of molten tin were struck by high-energy laser pulses.
Most of that energy is lost instantly. Only a very small amount of usable EUV light can be captured, making every photon incredibly valuable inside the machine.
What finally emerged was not the achievement of one inventor or one nation. It became one of the largest international engineering collaborations in
glitches. After decades of research, countless failures, and billions of dollars in investment, the impossible machine had finally...
Building the machine was only the beginning. The next challenge was convincing the world's largest chip manufacturers to trust a technology unlike anything they had ever used before.
The promise was extraordinary: higher transistor density, greater efficiency, and a simpler manufacturing process. Conventional lithography could still produce advanced chips, but doing so required increasingly complex manufacturing techniques. EUV offered a more direct path towards smaller features. The industry's biggest manufacturers reached the same conclusion. Future generations of processors would eventually depend on extreme ultraviolet lithography. Each successful improvement allowed billions more transistors to fit inside a single processor, expanding the possibility. Although these companies compete fiercely in the marketplace, many ultimately depend on manufacturing capabilities made possible by the same underlying lithography technology.
Once the technology proved itself in production, it gradually became one of the most important tools in advanced semiconductor manufacturing.
Every new generation of semiconductors quietly expands what humanity can build, from faster smartphones and life-saving medical technology.
Every new generation of advanced processors represents...
By solving one of manufacturing's greatest challenges, ASML quietly became part of nearly every conversation about the future of advanced... From the outside, it looks like another industrial machine. In reality, it is one of the most sophisticated manufacturing systems humanity has ever engineered.
An EUV system is not built from a handful of major components. It is an extraordinary combination of hundreds of thousands.
Many components operate with tolerances measured in nanometers. At this scale, imperfections visible to the human eye can...
Every wafer must be positioned with astonishing accuracy, while moving at remarkable speed. At the heart of the system, microscopic droplets of molten tin become an artificial source of extreme ultraviolet light through an incredibly controlled sequence of events. Only a tiny fraction of the generated light successfully completes the journey to the wafer. Every reflection,
No single discipline could build this machine alone. It exists because thousands of specialists solve thousands of individual problems over decades of collaboration.
Even delivery becomes an engineering project. The system is transported in specialized modules before being reassembled and calibrated inside the customer's factory over many weeks. Installation is only the beginning. Every machine must undergo extensive calibration before producing the extraordinary accuracy required for advanced semiconductor manufacturing. After decades of research, engineering, and persistence, the impossible had become routine. The machine once considered unrealistic.
As semiconductor technology advanced, it became clear that chips were no longer just commercial products.
Modern economies increasingly depend on advanced semiconductors. From healthcare and transportation to art. When semiconductor supply chains experience disruption, the effects quickly extend far beyond the technology industry, reaching manufacturers and consumers around the world. Building one advanced processor requires an international network of companies, suppliers, and engineering expertise. ASML became one essential part of that global network, supplying technology that supports leading-edge semiconductor manufacturing around the world. Demand for advanced lithography systems continued growing as manufacturers pursued increasingly powerful processors for artificial intelligence, cloud computing, and high-performance electronics. Every improvement in manufacturing expands what engineers can build next, allowing new generations of processors to deliver greater performance and efficiency.
The race has never been about building a single successful machine. It is about continuously pushing the limits of manufacturing.
For ASML, success did not mark the finish line. Every new generation of chips immediately stories. The world's demand for computing continues to grow, and quietly, behind much of that progress, one extraordinary machine.
Completing one extraordinary machine never marked the end of the journey. Almost immediately, engineers began working toward the next impossible challenge.
Every generation of processors demands even smaller features, higher transistor density, and greater energy efficiency.
For decades, semiconductor progress has depended on one simple principle: build smaller transistors. To continue that progress, ASML and its partners developed the next evolution of EUV technology, high-NA systems. Improving these machines is not a matter of making them slightly better. Every advancement demands new breakthroughs as artificial intelligence, scientific computing, and advanced robotics continue expanding, the demand for increasingly capable processors continues growing alongside them. No single breakthrough will define the future alone. Progress will continue through thousands of engineers solving thousands of difficult problems together across the world. One generation builds the foundation, the next generation builds something even more extraordinary upon it. That cycle has driven technological progress for decades. The most remarkable technology of tomorrow may already exist today as an unfinished prototype quietly waiting inside a laboratory.
The future of computing will not be written by software alone. It will also be shaped by the invisible machines and
every morning, billions of people begin their day without realizing how deeply modern life depends on technologies hidden far beyond everyday view. Behind many of these moments lies decades of invisible engineering. Progress is rarely created by a single invention.
Most people celebrate the finished product. Few ever see the extraordinary tools that made those products possible in the first place.
For the engineers behind these machines, success is rarely measured by recognition.
The greatest engineering achievements often become invisible. Once they work reliably, the world quickly begins taking them for granted.
The future of computing will never belong to one company alone. It will continue to depend on researchers,
Long after headlines fade and product launches are forgotten, the quiet work of engineering continues, preparing the next breakthrough long before the world asks for it.
ASML did not become extraordinary by standing in the spotlight. It became extraordinary by quietly helping others build the future.
ASML helped redefine how the world's most advanced chips are manufactured. But building the best machine has never guaranteed building the best processor. For decades, one company stood at the very center of the semiconductor industry. It built the processors that powered the personal computer revolution. But technology never rewards past victories forever. In this industry, every generation begins with a clean slate, and every delay carries a price. Once, Intel led the semiconductor world. Then, almost quietly, the future moved somewhere else.